Thanks. Heavenly Father, we thank you for this morning, afternoon, and thank you for the students. Pray that you be with us today. Help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. So did you guys vote in real life yesterday? You're going to?
I accidentally registered in my
I'm all for these apps that make people think that they can text their vote. I think if anybody does that, then they deserve their vote not to be counted. I think whoever invented that, brilliance. But anyway. Yeah. Yeah, I called my brother up about 6 or so, and I was like, and now Nate Silver says that Hillary Rodham Clinton's in trouble. Does that count? Because my brother buys into polls and stuff more than I do. So I've been I don't think they mean much this cycle, because every bit of conventional wisdom had been turned on its head at every stage. So anyway, so I promised you guys I would look at the solution with you. So I'll take 5-10 minutes here. Any questions about test 3? I know this may still be a little fresh. But the final is soon coming, and it would be wise to try to understand how to do these problems. Number one is number one, I gave you the nth partial sum. So the definition of series is what? The limit of the nth partial sum is the sum of the series if the series converges, right? If the series exists. So here all you got to do is take the limit as n goes to infinity, which makes this go to 0, and you get 3. And that's it. So a lot of you thought you thought about it. So if you thought about it, you probably thought wrong. Sorry, but it's true. By the way, there's some of you, we're losing some. Some of us have lost the will of fire in here, and we've withdrawn from the course. I would say that this is, I don't know, if you put this much effort into it, supposing you're not an honors student, so you're trying to game the GPA, whatever, setting those people aside. This is a course you need for your degree, right? I will drop test grades that are bad if you do well in the final. So there's really very little reason that you should drop this course going forward. I mean, you should do your best to try to get to where you need to be conceptually by the final, then you pass this class. I mean, all right? Now, the things that are hurting you in here, right? The things you don't know about Calculus 1, those will still hurt you in Calculus 3. So if you just barely eke by this course, suppose you're that person, it's not really this course you should study. You should go back to Calculus 1 and try to own it before you go forward. That's really what's going to hurt you going forward. All right? Just a word of advice. I mean, ideally you do that before you're done in here. You don't want to continue to, sort of pay tax on things you've already been taxed, right? Sorry. So this one's just nth term test. That goes to 1/3, which is not equal to 0, so that diverges. This one here, like I told you guys once or twice, if I see a factorial, I think ratio test personally. And so ratio test, in fact, goes to 0. I docked you guys a little, not this was worth 10 points. I think I docked some of you 2 points. A lot of you, when you put n plus 1, you just put n plus 1 here. So there's a variety of different things that happen, but it's 2 times n plus 1, right? So that results in a 2n plus 3 factorial there. 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So you're actually left over with 2 things down here in this problem. And not all of you, this is one of those errors that you might have overlooked and still got the problem mostly right? So it's kind to you in that sense that it won't make you reach the wrong conclusion. But still, that's an algebraic oversight that you should think about, right? See what I'm talking about? You have to think about putting n plus 1 into whatever you have. You have to really think through that. What does that mean what does an plus 1 means? It means everywhere there's an n, I replace it with n plus 1, right? So that plus 1 gets multiplied by the 2 just like n does, right? Any questions? I think you guys had more trouble with the next one. And I know a lot of you just lost a lot of points basically because you were lost, right? So I wrote a question mark on your solution. It probably means I'm like, what? So if you are convinced that you are right and you want to argue with me about the question mark, you're welcome to do that. Anyway, so here we know that sine is between -1 and 1. So if you just add 2 to this inequality across the board, we get 1 is less than or equal to 2 plus sine n, which is less than or equal to 3. So this term is positive, right? Which means that this is a positive term, which means we have a positive series here. Now, you shouldn't assume that from the outset, of course, because sine could be negative. But anyway, it turns out that this is a positive series. And so I can compare it, direct comparison to 3 over n to the 1 plus 5. That converges by p equals 1.5 times 3. And so by direct comparison, that converges. Limit comparison, I just don't know if that was, I don't know. I'm not sure about limit comparison there. This one, hey, a lot of you got this right. I was very happy. Generically speaking, most people got this problem, which was a welcome sight for me. Some of you saw through my subterfuge here. I only made it worth 5 points because I didn't want to dock you like 10 points if you just didn't see it. And let's face it, this kind of problem, it's a question of, do you see it for what it is, right? There's no algorithm. The only thing that really can make you better at this is more familiarity with what the form of power series are, recognizing them when you see them, right? So that's kind of that's why I only made it worth 5 points and not more, because I know some of you aren't going to see it and I don't want to hit you that hard for it. But it is something I'd like you to be aware of. Any questions about this? Oh, and then e to the log 2 is 2. So, yeah. This one here was what? This one was very, very close to what? One of the problems that I had on the what? Practice test, right? The exact same problem? Is it exactly the same? It might be exactly the same. I switched up the numbers. Okay. I thought I did something to it, but not much. Anyway, ratio test gets you most of it. We need that that's less than 1, which gives me that x minus 3 is less than 1/2, so the radius of convergence is 1/2. Then you got to check endpoints. One gives you an alternating harmonic series. The other one gives you the harmonic series. So you gain one endpoint, you lose the other. And there it is. So that's pretty standard one of those problems. This problem was there, right? Again, that's just like the thing I had on the quiz, but I changed the numbers to protect the innocent. Any questions about this one? Again, the point of divergence tells you that it has to diverge past that point, right? Whereas the point of convergence tells you everything, everything closer than that point of convergence must also converge, and that's the guiding principle. This geometric series, basically, it's kind of funny. This doesn't always have to happen, but I had like 2 problems on this test where I ended up having A and R be equal. It's just a quirk. Actually, this one was minus 5/8, I guess. But I mean, I don't know. It's just kind of funny. So this is x squared over 3 is the A, quote unquote, here for the geometric series. R is x squared over 3. So it's geometric. I need that the radius is less than absolute value of the radius less than 1. So that gives me that the absolute value of x is less than root 3 after I take the square root of that. And so x has to be in here. And there it is. So I just have to, and this is not, like I probably took off a point if you wrote that, because this is not a power series, right? What's a power series? Power series is coefficients times power functions. This is not yet that. There's work left to do here. You have to simplify this to that before you have a power series. Sorry, but it's what it is. It's like, I don't know, it's like you make an agreement with your neighbor that you're going to shovel his driveway for $10, and part of the agreement is that you shovel his sidewalk, and then you come to him and you say, I've shoveled your driveway, where's my $10? And he's like, I'm only going to pay you $8 because you didn't shovel the sidewalk. It's kind of like that, That's the sidewalk, like from here to here. You got to clean it up. Oh, yes. As you can see from the green, I neglected to put the minus in the radius to start with. Yeah, I did that. I was like, man, why are you guys all making the same mistake? What's going on here? And I was like, wait a minute. It's me. I'm the one. All right, so yes. Anyway, so differentiate, that gives you something that's geometric. Identify that A is 5/8 and R is minus 5/8 times x minus 1. Do the geometric series, shovel the sidewalk, and then you integrate to get back. That gives you a constant here. You fit the constant by plugging in 1. That gives us log 8 equals c, and there's the answer. This is very, very much the same problem as the one we had log 10 in the quiz, right? I wanted a Taylor series problem that was easier than the quiz problem. That's what this is. On the quiz, I ended up with something like x squared times sine, and it was a mess. So I thought, if I make it just tangent, then you can differentiate tangent pretty easily up to second order and plug in 1, and then there you go. That's the, Taylor series centered at 1 for tangent, just that. And if you wrote this in terms of sines and cosines, that's cool. I mean, you could convert tangent to decimal and secant to decimal. I would have been fine with that, but I also would have been like, why are you wasting your time? But because I don't care about that. But of course, your employer might. All right. Anyway, I don't pay you money, so there's your clue. Let's see here. So here, basically, you got to find the power series for that, and then you integrate term by term. There are various ways to do this. I chose to divide the cosine series into 1, and that gives me 1 plus 1/2 x to the 8th plus 5/24 x to the 16th. And so then multiply that. So basically 1 over cosine x to the 4th is this series, and then multiply by x to the 11th. It just multiplies x to the 11th term by term. And so that gives me this to integrate, and then I just integrate 1/12. 2 times 20 is 40, and come on, obviously 28 times 24 is 672, and there's 5, and so there you go. The first 3 terms plus plus. I usually write this. I would prefer to have written this constant up front, but I already wrote the 12th here, and I'm writing in pen, so I had to commit. I just committed to writing the c over there instead. It violates my generic stylings for answers, but on the other hand, I found that if I write in pencil, it just never scans very good, so I just try to get in the habit of writing in pen for my solutions, but it does make trouble for me sometimes. This problem was not impossible, despite the fact I hadn't talked a lot about it. You have all the tools you needed to solve this problem, but admittedly, this may have been a new problem for you, right? Although I do think there were problems in the homework that I have solved and posted for you guys that were like this. So basically, the point is it's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So it's 1 over 123 over 1,000 plus 123 over 1,000 times 1,000, right? Basically, it's 123 over 1,000 plus 123 over a million plus 123 over a billion, right? In American lingo. And it's a geometric series. The ratio is 1 over 1,000, and A is 123 over 1,000. So there it is. And then I just shovel the sidewalk. So 123 over 999, which is obviously, well, I don't know. My calculator told me 41 over 333. I don't know if I would have seen that. Maybe I would have seen that. I don't know. Depends if I'm looking for it or not. But anyway, cool. Any questions? So any repeating decimal you can play this game on, right? There's the proof, basically, that any number with a repeating decimal expression is in fact a rational number. It can be written as a quotient of 2 integers. Geometric series proves that. This is pretty much your plain Jane alternating series estimation question. Sometimes I ask this question packaged with an integral. I took the integral away and just gave you a raw alternating series to work with. And so basically the point here is 1 over 720, 0.001. So like, that's a little bit borderline. Certainly if we go to 1 over 9 factorial, that's definitely small enough. And so I just kept the first 3 to be safe. 1 minus 1, 6 plus 1, 720. That gives me 601 over 720, which is about 0.83472. If you said like 0.84, I was pretty chill. Like I was like, yep, okay, I'm going to give you credit. So I was pretty lackadaisical on this problem, much more so than others. Anyway, but really, you should have told me by the alternating series estimation theorem. I think a lot of you didn't do that. I should have taken off a point. I might not have. But anyway, what's done is done. So here we go. Here's your function. Find the derivative, 56th derivative, in fact, evaluated at 0. This is irrelevant, right? The question is, can these produce 56 order terms, like x to the 56? Well, yeah, you can. I can just take a 2 here and a 54 there, right? Or this one, can I get 56? Yeah, sure, choose j equal to 7. That'll give me 56. So conceptually, this is the same problem as the quiz, but I changed the game a little, right? In the quiz, the x to the 100 mattered, but like the cosine didn't matter. Then the test, it turns out the exponential and the cosine matter, but the x to the 100 didn't. So anyway, basically by Taylor's theorem, we get the 56th derivative at 0 is this stuff. So if you're interested in the numerics here, this is like nothing, right? I mean, like 56 factorial over 54 factorial, that's tiny compared to 56 factorial over 14 factorial. This guy is much bigger. So, oh man, come on. Yeah, negative. But anyway, so. Yeah, so as I have it right now, it's very, very wrong. But, sorry. Well, I mean, it's missing a minus. But anyway, any questions? So the final is comprehensive. The stuff I just talked about is part of it. It's not all of it. The final tends to be more about integration than anything else. So, you know. All right, so curves. So I just want to just take a second here to talk about chapter 12 in my notes. I would like you to read it. Please read it. I basically, in this chapter, described 3 things. The graph of a function, right? You guys know what the graph of a function is? Set of pairs x comma y such that y is equal to f of x. This is an old story. You studied it before. A level curve. This is a little bit weirder, but should be starting to be familiar to you. Basically, you're looking at a function of 2 variables equal to a constant. This is just a fancy way of saying a level curve is the solution set of some equation. Like x squared plus y squared equals to 10 is a level curve. It's also a circle with radius square root 10, right? And then the new thing, parametrized curve. So here we're looking at the set of points x of t comma y of t, where t is some parameter ranges over some subset of the reals, all right? And if you read my chapter here, I go through and I talk about, the shortcomings of graphs and the structure of level curves. Here's some level curves can be all kinds of crazy stuff. Let's check this out. Oops. If you look at the solution set to this equation, x minus y times x squared plus y squared minus 1 times x minus y times xy minus 1 times y minus tangent x equal to 0. This is a level curve. It also looks like this. So like pretty much a standard silly trick you can do is if you have the equation for 2 level curves, if you put them both equal to 0, right? You just multiply the equations, then you get both level curves. So combining level curves is as simple as just multiplying the equations which define them. I don't know if you've thought about this before, but, well, I mean, probably not, but anyway, level curves can be all kinds of crazy stuff, right? So, if I asked you to find a parametrization of this curve, that would be awful. I mean, you'd have to ask me which part, right? Because you'd need a different parametrization for like this piece versus that piece versus this piece versus that piece, right? And like parametrizations would pick up pieces of this, but you'd probably actually, in terms of formulas, you would need different parametrization for different pieces here, right? Just saying. This is called the, this right here is called the where is it? Words. Do I gotta give it a name? Implicit function. Have I misspelled that? No, it's okay. Implicit function theorem. Basically what it says is if you have a level curve, then you can solve it locally as a function of x. Like you can find y equals to f of x, which when you plug it into here, it works. Provided you have this condition. You need the partial derivative of f with respect to y is non-zero at the point. I know you guys don't know what partial derivatives are yet, but that's kind of the point, is to describe when you can solve a level curve in terms of a function of one of the Cartesian variables. That's really a question that's a little bit past Calc 2. And yet it's kind of interesting because we're thinking about level curves, and so it's a natural thing to think about. But anyway, this is a result from advanced calculus for what it's worth. But all right, again, I just would ask you to, here's an example of that. So the circle has x squared plus y squared equals to r squared, right? And these points are the points where the partial derivative with respect to y is 0. Those are exactly the same points where I can't solve for y as a function of x near the point because it automatically fails the vertical line test. So that theorem kind of picks up on those points where you have vertical tangents or some kind of trouble solving for y as a function of x in the level curve. But I'm sorry, let me put this away here. The other way to think about paths is in terms of mappings. So like a circle, you could think about, this is a good way to think about parametrizations, is you think about the real line as being like a string or something, and then what the parametrization does is it takes that string, you think about it being stretchable, and it just kind of like lays it out over the curve, and that's what the parametrization is. To make this idea better, I should make this line, as long as the circumference of the circle, but then my picture gets to be too big. So, well, maybe it wouldn't be. Poor planning on my part, I guess. But so this is one way to think about parametrizations actively. Think about it as it's a way of finding formulas which basically encode taking a piece of string and laying it along the curve, whatever it is in the plane, and for each point as you go along the string, that's t increasing. So t doesn't have to have anything to do with x or y. It just tells you about your progress along the curve. This is the nature of the parameter. So I have some more examples, some more pictures in here. I'm going to put this away. Sorry, I got the thing open and it started on this projecting. It's hard for me to stop. It's kind of like a drug, which are apparently okay. So. Let's see here. Let me put this away. All right, so what did we get to last time? My point to you is if you read chapter 12, it should give you a better geometric sense of what's the difference between a function, a level set, and a parametrized curve. These are really three competing ways of looking at curves in the plane. Right? They're interconnected. They're not mutually exclusive. And the new player to the game here really mostly is the parametrized curve. All right. So last time I started showing you how to parametrize different curves. Let me add one more example to that. So the example I wanted to go over was to find parametrization I can't decide how to spell parametrization all of a sudden. Some people spell it with a Z, some people spell it with an S, but I'll spell it with a Z. Parametrization of, and here's the thing we're going to look at, hyperbola centered at, let's say, -3, 7, which opens vertically, right? let's see here. So we draw a picture here. -3, 7. So something like that. And I'm going to assume that it has, its asymptotes have slope 1. So in other words, I'm assuming that the asymptotes are like these guys, basically. All right, so here's now if you think about what the asymptotes having slope 1 means, I guess it's not entirely clear. I'm not sure I'm making. I'm worried I'm describing more than one hyperbola is my concern, but anyway, the hyperbolas I'm talking about are these guys. Come on. Something like that. Now, what are the equations for these red curves I just drew? What's the equation, rather? Start us out, x plus 3 squared, and then we've got a y minus 7 squared. I'll put equals 1 over here, if I do that. I could put a 1 over there, I could put a minus 1 over there. I mean, it kind of, how you want to look at it. If I put a 1 there, what do I have to, what line does this not cross through? Think about it. If you think about this hyperbola doesn't go through here, right? That's what? That's y equals to 7. So when y equals to 7, we want there to be no solution, right? So if y equals to 7, that makes this term 0. What has no solution? It's when we have a negative number equal to a positive number, right? Non-zero number. So if I put a minus here, and if I put a plus here, I think we're in business. See, because when we put y equal to 7, I get minus x plus 3 squared equals to 1. There's no way you can solve that with real numbers. So that's the equation of a hyperbola which opens vertically and has center minus 3, 7, and has very boring plain Jane asymptotes of plus or minus 1 slope. How do I get non-1 slopes? If I want different fancy schmancy slopes, all I do is I take this expression, right, and I divide this by a number. I divide that by a number. If we divide the quadratic terms by some number, then the slopes will kind of like go squishy one way or the other, right? Okay, so anyway, now we found the curve, right? So here's the description of the curve. This describes the solution set to this is the hyperbola, right? So what kind of description is this? This is a level curve description of the hyperbola, all right? The level function here, what's the level function? F of xy equals to what? You know, it's minus x plus 3 squared plus y minus 7 squared. So if that's the level function, this is the level 1 curve of that function. Fixing the level function rather, if you look at the level minus 1 function, that would give you a hyperbola which opens sideways. So once you fix the level function, the positive levels will give you like vertical hyperbolas, and the negative ones will give you the horizontal hyperbolas, horizontal opening ones, and which ones are which depends on how you define the level function, right? Anyway, so what's the parametrization of this curve is my question. Your question should be which curve do you want, right? If you have a disconnected curve, right? If you have a curve which has two pieces, which are just not together, You're going to need two separate formulas for those. Yeah. Oh, okay. So that's fine. You guys pick it. You want to do the upper half or the lower half of the hyperbola? The upper half to start with? Okay. So let's find a parametrization for the upper half. What would it be? Parametric formulas for upper half. Let's see here. So what I'm going to do, what I'm trying to deal with here is y minus 7 squared minus x plus 3 squared equals to 1, right? So this makes me think about cosh squared t minus sinh squared t equals to 1. I know that identity, right? So natural choice, y minus 7 equals cosh t, right? Or y is equal to 7 cosh t. 7 plus, sorry, I'll get it right eventually. 7 plus the hyperbolic cosine of t. And x is equal to minus 3 plus the hyperbolic sine of t. And that's for t, a real number. And there you go. That's the scalar parametric equations for the upper half. Just like that. You can verify that if you plug those in, they solve the level curve, and we've got it. Excuse me. So then what? How about the lower half? I'll do it here. Lower half, I would let x equal to, same thing, minus 3 plus the sinh of t. And I would let y equal to what? So, yeah, 7 minus cosh t will do it. And that's for t, an element of the reals. AKA minus infinity less than t less than infinity, if you like that notation. All right? So I hope I've showed, I want you to read chapter 12. In chapter 12, I give you many more examples on how to parametrize specific ellipses and hyperbolas and other things, all right? I'll do one more example here that's not one of these standard, these are conic sections, right? If you take a cone, how do you get a cone? A cone is just formed from taking sort of, well, how to say it? It's a cone. I don't know. If you take a cone, which mathematically is a double cone, all right? So one of these guys. So if you take one of these cones, these mathematical cones, which are double cones, and you imagine slicing that with a plane, right? The intersection of the plane and the cone is what's called a conic section. Section is a word for cut. So if you cut the cone with a plane, the curve of intersection is called a conic section. Conic sections, depending on how you cut it, give you different things, right? Like pretty obviously, if I take this, right, and I cut it like that, what do I get? I could get a circle. If the plane is a little bit tilted, what do I get? An ellipse, right? If I, on the other hand, do something like, oh, I can't draw it. If I could draw it. I'm trying. It's bad, but I'm trying. So like something like this. I don't know. I can't draw it with anything. I'm drawing a strip, but you should think of it as an infinite plane, right? And this cone goes on and on. So if you could picture it more fully, you'd see that you get something that's like that, you know. So these sort of vertical planes, as you move them around, give you hyperbolas, right? Anything else? What's that? Parabola. How do I get a parabola? I believe you. I'm just trying to remember how to get it in the picture. It's what? Parallel to a tangent. Tangent plane of a cone. So if I do something like, it's got to be in between the blue case and the green case, right? If you could somehow imagine sort of tilting the plane. You keep tilting and tilting and tilting and tilting. Eventually, you have the plane kissing the cone. It doesn't. Just cuts one.
So like that's why we had just parallel to the slant of the cone, but so it only has to the top part. Yeah, like a line like that.
Oh, like that. So you're saying it's something like, I don't know, I can't see it in my mind's eye. It's my problem. I think it's mostly my problem though. So it's like this. Let's forget it. Let's forget this picture. But anyway, there's a section in your book with pictures which are hopefully convincing, even if I'm not. Anyway, don't worry, there's no earthly way I know to test this, so you're safe. Mostly I just want you to know there's something called an ellipse. There's something called a hyperbola. There's lots of twists and turns on these things, right? And you should be able to parametrize any of them. All right? And within reason, you should be able to actually pick out just little pieces of them too, right? Like if you just wanted to parametrize, for example, what if you just wanted to parametrize, say, the upper half, but just the right half of the upper half here? What if I just wanted this piece? What would I do? Right, I would cross this out and say, nope, 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 just t greater than or equal to 0, right? How do I know that? I know that because I know how cosh works. Excuse me, I know how sinh works. Sinh is positive when t is positive. So the formula here is minus 3 plus sinh. So if I want to go from minus 3 onward, I just make sinh, just take positive, or rather non-negative entries, and that goes from minus 3 onward. This is how we have to think about parametric formulas. All right, anyway, another example. So, there's other things out there. You could have something like x squared plus x to the fourth y squared equals to 7, right? And you could say, find a parametrization of this. Well, I don't know if, I mean, finding parametrizations of curves is an art. All right, it's not like differentiation or even integration to a certain extent. It's really much more adventurous than that. So I've been showing you how to paint some standard pictures, let's say. This is not really one of those. So, left to my devices, if I'm lazy, what I'll try to do is just either use x or y as a parameter. Or, I don't know. So here, if we let x equals to t, right? Then what does that make y? We've got t squared plus t to the fourth y squared equals to 7. So you can solve for y, right? T to the fourth y squared is equal to 7 minus t squared. And so y squared is equal to 7 minus t squared over t to the fourth. Well, that's going to have trouble. T not equal to 0, apparently we need to assume, right? And so that implies what? That implies that y is equal to plus or minus the square root of 7 minus t squared over t to the fourth. So apparently this curve has two pieces, right? It's got a piece with positive y, it's got a piece with negative y. And the algebra has guided me to find parametrizations for both. But we've got to make a choice. A parametrization is a function, all right? So like, if we're looking for the parametrization, so for let's say for y greater than 0, we can let r of t equal to t, comma, square root of 7 minus t squared over t to the fourth. All right. For t not equal to 0, parametrizes the curve, right? That's going to parametrize the part of the curve which is in the where y is positive. If I want where y is negative, I just do the same thing, but with what? With a minus on the second thing.
Where that goes imaginary.
What's that?
What about for t greater than or equal to the square root of 7?
Oh, right. Yeah, I should be more careful. Let's see here. Let me think about this geometrically for a second here. 7 minus t squared is, it's like that. So this is 7 minus t squared. So, okay, so basically, I'm looking for square root of 7. Square root of 7. So I guess, to be more specific, I should really do square root of 7 to 0, not included, union with 0 to square root of 7 included. I mean, the formulas will at least make sense for those. I'm not sure what happens. What happens at t equals to 0? Oh, t equals 0 is a point not on the curve, right? T equals 0 is x equal to 0. Does x equal to 0 have a solution? No. Check it out. I mean, like x equal to 0 here gives me 0 equals to 7. So that's actually not some point we're missing. That's a point not on the curve. We're not missing anything by excluding 0. But otherwise, if t is in here, right? If t is in here, if I plug x equals to t and y equals to that into that equation, by the algebra we just did, it will produce 7. So, I'm kind of curious. Want to see what this looks like? By the way, I have not said much about technology in here, but it really is important that you use some kind of graphing thing to gain more geometric intuition for what you're doing in chapter 10. It's really important to be using something to plot things that you're looking at, all right? That won't solve problems for you, but it'll help you understand what you're doing more deeply. There's a lot of different things out there. There's Mathematica, if you have time to get it on your machine. I don't. So I'm lazier. I will do something like, I don't know. I could do the Wolfram Alpha. Sometimes that's helpful. I also like another grapher I'm fond of is, oh man, what's the name of this thing? I mean, of course, Dr. Wang is big on the GeoGebra. I don't like GeoGebra that much for what we're doing here, though. I want to say maybe D. Desmos, that's the one. Yeah, start graphing. Come on. Is it showing? All right, so what was our equation? I've covered it up, haven't I? Oh, no. What did I just say? You said x squared. So there it is. As you can see, something wacky happens at x equal to 0, right? It's got vertical asymptotes. That's why we couldn't touch x equal to 0. That makes sense. And on the other hand, so the plus and minus solutions actually join together here. So you could do it like case-wise. I mean, like if you wanted to parametrize either the right or left half, you could use plus for the top, minus for the bottom. And this would just be like let t range from 0 to root 7. So anyway, that's kind of neat. I think you can add item. Oh, come on. X equal to t. Y equal to, what was our formula? Square root. course, you know, I had to spend. Come on, what's wrong? I don't understand this. Well, you're dumb. Let's see here. I mean, you don't understand this. Well, figure out how to understand this. Let me try something else. Let's put it in some parentheses. Now I'm understand this. Haha. 0 is probably bad. Let's see. Can I make that? All right, here. Let's cheat the system. There we go. And we said what? Square root of 7, which is what? Seven to the 0.5, yeah? All right. Oh, and check it out right here. See that? That blue? Now, I could do something more fun. I could even add A. I said A. I said A. No, I don't. You come on, you A. Nope. How do you? No! Come back to us. No, I don't. That's the opposite of what I want to do. I'm trying to make this into a slider. How do you make it into a slider? You guys know about sliders? There is such a thing. I know. I've done it before. No, that's not what I want to do. Here, tell you what. I'll look at something else. Whee! See what happens when you change A? See what happens when you change B? Like a so. So anyway, these are kind of fun. Yeah?
Do you just click on the symbol and change that?
It'll animate it. Woo! It's not that hard to add a slider. I just am forgetting whatever stupid thing to do. The Google.
Do you have to make an account for this? Or?
Yeah, it costs like $0. This guys is a solution to a wave equation I found, and then I took the solution and I animated it. Whee! It's like a wait, take a string and give it a, and that's actually. I mean, I solved the partial differential equation, and that's the solution that came out. But. All right, guys. I seem to have devolved into some sort of nerd show and tell today.